Okay, I hope I hope you can hear me.
Yes, I can.
Okay, thank you very much. Before we start, I wanted to say some words in Polish at first. Szanowni Państwo, drodzy studenci, pracownicy naukowi i przybyli goście. Nazywam się Tomasz Kowalczyk i jestem prezesem koła naukowego Analizy Danych na Uniwersytecie Ekonomicznym w Krakowie. Bardzo serdecznie dziękuję za przybycie dzisiaj na to spotkanie. Bardzo się cieszę, że mogę z Wami uczestniczyć w tym wyjątkowym wydarzeniu, spotkaniu z profesorem Bruce'em Hansenem. Jest to jednocześnie ósme, ostatnie w tym roku akademickim spotkanie otwarte w ramach cyklu, utworzonego przez nas cyklu wykładów otwartych pod tytułem Dane są wszędzie. Jesteśmy niezwykle wdzięczni każdemu z Was za obecność na wszystkich poprzednich spotkaniach i dziękuję również wszystkim prelegentom oraz osobom wspierającym cały ten projekt. Dzisiejsze spotkanie jest zwieńczeniem bardzo udanego roku naszej społeczności, a kończymy je mocnym akcentem. Serdecznie witam naszego prelegenta, jednego z najpopularniejszych badaczy i ekspertów ze świata ekonometrii i statystyki. Kwestie organizacyjne, o których też za chwilkę jeszcze powiem w języku angielskim. Przygotowaliśmy platformę Slido, która służy do sesji Q&A, jeżeli nasz gość będzie miał kilka minut na odpowiedź na Państwa pytania, to za chwilkę na czacie wyślę link do właśnie tej platformy i bardzo byśmy prosili o zadawanie pytań właśnie tam. I think I can switch to English right now. Dear students and academics and visitors, thank you very much once again for joining our meeting, as this is the unique event, a meeting with Professor Bruce Hansen, as this is the last open meeting in this academic year within the program, within the project called Data is Everywhere, the series of open meetings. We are extremely grateful for each and everyone who was able to attend during these lectures, and we sincerely thank all the speakers and supporters of this project. And today's guest is, as I said, unique, Mr. Professor Bruce Hansen, who is one of the most popular researchers and experts in the world of econometrics and statistics. He will give a lecture entitled "A Tale of Three Econometric Stories: How to Learn about Causality from Data." On an organizational note, please feel free to ask questions via Slido platform, which I will give the link in a second. And if the professor has a few more minutes after the lecture to answer the questions, if any will occur, this will be good base for selecting the questions. If you have any suggestions and questions, I remain at your disposal. And I think it's time to give the floor to our speaker. So, Professor, the floor is yours. Thank you.
So please do ask your questions. And also let me know if you don't see my slides or hear me, because I wanted to get that corrected. But thank you very much for attending today. Hopefully this will be a useful talk for everybody, including myself, and we'll learn a little bit about econometrics. So my area of research is econometrics. For those of you who don't know, I've recently written a textbook, which the material I'm going to be talking about today comes from that textbook. And so if you're interested in more the details, that's the place I'd like to refer you to learn. I'm going to be talking today about causality and how to learn about causality from economic data, with the intention of thinking about your future research projects, giving you ideas about how to frame economic research using econometric methods. And it's going to be a quick overview. Hopefully in 1 hour, we'll talk about a few ideas. So when I say about causality, what we're interested in is how one thing changes due to a different change. If you change tax policy, what is the impact on economic outcomes? There might be different economic outcomes we are interested in, but in general, we're interested in that if you change something, how does something else change? And so typically, for many issues, we're interested in changes in policy. and then how do outcomes in the world change in response. So as econometricians, now we want to say, how can we learn about these issues? How can we learn about causality? How can we learn about how Y responds to X from data? Okay, an economic theorist might be interested in this in the context of a model, while an econometrician is going to be asking the question, how can we learn about this from data? So in the sub area, what we might call causal econometrics, we're trying to learn about causal effects from economic data. And today what I will do is talk about three, I'll call them stories, about causal economic inference, describing the three major techniques that are used today to do what is often called causal economics. And they are instrumental variables, difference and difference, and regression discontinuity. And I'll be illustrating all this in the context of three examples using three primary examples from the economic literature. The first is the effect of education on wages. The second is the effect of the minimum wage on employment. And the third is the effect of a program called Head Start. So let's start with the first story, the causal effect of education on wages. This is based on a famous paper written by David Card, published in 1995. And this is, if you are not aware, David Card won the Nobel Prize in economics recently for his work on labor economics, and primarily for his innovations of trying to bring in the study of causal economics, and sometimes called a credibility revolution, into labor economics. And this is an illustration of the method known as instrumental variables, a very old technique. And I'm sure most of you are familiar with instrumental variables, and it might sound a little bit boring to rehash this, but I think that going through this carefully will put it in the context of linking this to the other ideas. So what is the primary idea? The basic premise goes back a long way in economics that says that models say that education impacts human capital, which we often in economics will describe of the accumulation of our knowledge about how to do things, and thereby increasing marginal productivity of labor. And in a competitive market where you're paid competitively, that will increase your market wage. It will also increase the output. Okay, that's the basic idea of the effect of education on wages. And it's viewed as in economics as a causal effect. If we increase a person's education, they will have more human capital, and they will become more productive, and they will end up earning more in the labor force. So that has a prediction that in data, we should observe that people with higher education should be receiving, on average, higher wages. And when we say on average, it's because education is not the only determinant of productivity. It's not the only determinant of the wage one receives. There are many other determinants. And in fact, in the data, we know that those other determinants have much greater variation than education alone. But it's still, in the sense of a regression, we would expect that education would be predictive of wages. So, as I said, there are many other factors that influence one's wage. And one of the we might think of as a key factor in many, at least competitive economies, is individual ability. Individual ability is a very complicated concept, but at a fundamental level, we would think it from the standpoint of an econometrician is unobserved. I do not see in the data someone's ability. What I see in the data is perhaps your education levels, your work experience, and other general factors, but I might in some data sets have particular test scores, but I don't really have a direct measure of a person's ability. Ability is a complicated concept. It includes a person's intelligence, work ethic, physical skills. There's different types of ability, and that they might play into different roles. But we still have, I think intuitively, we all understand that different people have different abilities. But the main point is that wages are not fully explained by education and other observables. It also is explained by unobserved factors. And we like to think of it from a modeling viewpoint is that unobserved component is random. Now, economic models also say that people know something about what is going on in their lives, and they will make choices regarding their education. For those of you in the audience who are students, you are choosing to get education. You are not choosing education randomly. You are choosing education based on knowledge of yourself and your abilities and the gains that you will achieve due to education. And so you are going to self-select into higher education if you are a high ability person. So an implication is that education itself is a proxy or an unobserved explanation for unobservability. That is, if I see someone with a lot of education, they are likely to be not only well educated, but they're also likely to be a person of high ability. So that would suggest that the correlation of education and wages is going to be a combination of two things. It's a combination of the causal effect of education and wages, and also a combination of the proxy effect of the fact that education occurs because of your high ability. As a consequence, a simple regression of education on wages, or wages on education, excuse me, will misstate the causal effect. Let's see this in terms of the mathematics. If you write this down in the standard econometric equation, y equals alpha plus beta x plus e, and for simplicity, just think of 1x. We'll have extra controls in practice, but think of it as simple. Y is a wage or a log of the wage. X is education, some sort of measure of how much schooling you have, and E is all the other factors. And we want to think of beta as the causal effect, that if I change your education, what will be the impact on the average wage? If you take a standard econometrics class, you start out with classical assumptions, which has at the core that E is either independent or uncorrelated with X. And this is written down as some sort of a starting point. But what that does is it negates a lot of the structure of where the data actually comes from. But once, anyway, you assume that E is independent or uncorrelated with X, you say, I'm going to estimate by beta by least squares. And we have a sort of theory to help explain this. But the problem is that at the core is that when you think about the structure of that model, unobservability is all in E. So y equals beta x plus E. E is the part of the wage that's not explained by education that includes our unobserved ability. And that captures our choices about that captures our the ability is correlated with our choice, so it's correlated with X, and so X and E are correlated. That violates the classical assumption. And one way we phrase that in standard economic language is to say that education is endogenous. Now it's better to actually say what it's endogenous for. It's endogenous for what? For wages. Education is endogenous in a model for wages, because we know that the error term in that equation will be correlated with the right-hand side variable education. And we know that from basic econometric methodology that least squares estimation will be inconsistent, meaning that even if very large samples, you won't get close to the true parameter estimate. The parameter estimate won't be close to the true value. People will informally describe this as a bias in the estimates. So what do we do about it? Well, a traditional solution is not just due to David Card, but a traditional solution is to use instrumental variables. And that's the first tale of causal inference, is to think about coming up with an IV, an instrumental variable, which will help us learn about the causal effect. So what is the method of instrumental variables? You need an instrument. We call it in the language of math Z. And it's something which is correlated with the right-hand side variable X, but uncorrelated with the error term E. So that's the language of kind of bread and butter econometrics. But in the language of causality, what we want is a variable which has a causal effect on the regressor Z, but has no direct effect on the outcome Y. So in this particular case, we want to find a variable which affects your education level, but has no effect on wages directly. It has an effect on wages indirectly through education, but not directly. And in this idea, it's the identification or the ability to identify that this is a valid instrument all comes through economic knowledge, not really through data itself, but through knowledge. So to get the part of the idea for that is to step back a moment and to think about what we would like to do ideally, and then try to think about how to proxy this in practice. And the ideal, often in scientific studies, is to have a random control trial. RCT is the standard definition. In some ways, this is viewed as a gold standard for learning about economic outcomes. So if you want to learn about the effect of education on outcomes, the RCT approach would be to mandate different levels of education for different groups of people. So what you would do is you take a population of young people. Perhaps you're looking at the impact of college education. We would we take a group of people with high school education, and then randomly divide that group of people into two groups, called one control and one treatment. Tell the control group, nah, you can't get any additional education. You go into the workforce and that's it. Take the treatment group and tell them you must go get a university education. In the United States, we often call that a college education, because it's referring to the education before graduate education. So college education, you must do it. It's not a choice. You must do that. So we now force these people into these two sets of education decisions, then wait, say, 10 years to see what transpires, and then come back and measure what wages they received in the labor force. And then if everyone adhered to this mandate, we would then have a measure of the causal effect of college education in a general population, or at least in the population from which we did the sampling of youth. But as we described that, it's fairly obvious that this random control trial is simply infeasible. It's not, would not be allowed by law. It would not be allowed by ethics. It would, and even if you try to do it, there would be reasons why one would expect that people would deviate, they would cheat in one way or another. So the plain fact is that observational data is not a random control trial. We can do random control trials in very narrow contexts, but often the context of major interest, we can't do things randomly. We have to get by with what we observe. And part of the reason is fundamentally that people select their levels of education subject to constraints that they might see in the world, but we fundamentally do not have randomly assigned education. A concept pushed a lot by this recent literature on causality is to think about a natural experiment, as opposed to a random control trial, to think of a natural experiment. Natural experiments use observational data, but focus on the context where there is a measurable exogenous effect on people, which induces a separation, might be partial, but a separation of people into effectively control and treatment groups. If we have a natural experiment, and this is the core key to understanding causality in these contexts, then we'll be able to do estimation of causal effects, and this measurable effect can be the instrumental variable, which I've mentioned before. And then we can measure this causal effect by looking at the effect on the desired outcome through the instrumental variable. So if we can see a variation in the world which I don't have an impact over, but it impacts me and it impacts the level of education I'm able to attain, then we can use that as an instrumental variable. So what is the example that So I think the easiest way to understand this is through examples. Different people have tried different examples. David Card, in the paper I referred to, used the idea of proximity. So proximity means how close, distance, okay? So as I mentioned before, in the United States, where this data set was gathered from, we often use the term college to refer to education beyond high school. Most often in Europe, that is referred to as a university education. So I'll be using these terms interchangeably. So it means typically the 4 years of education between the ages of 18 and 22. Now, the idea of proximity that David Card came up to is that not everyone lives near a 4-year college. Some people live at a great distance, some people live close. So we're thinking here about youth, thinking about people who are about making the choice of going to university, 18 years old, 17, 18 years old. Some of those people live in cities where there is a major university or a minor university or some sort of a college to attend. And some people live in a more rural setting or in a small town or a smaller city where there is not a university or a college. What does that mean is that for people who live close, they may have a lower cost of attendance. They can live at home, they can stay with their families. The mental cost of thinking about changing a location is small, while people who live a far away distant might find it more challenging. They have to go live with a relative, they have to go rent an apartment. It's not as commonly done, it's more costly for them. And since we all understand that costs affect outcomes, a higher cost means you're less likely to attend. So what this predicts is that the distance from the closest college is predictive of the negatively predictive of whether or not you actually will attend. Now you might think, well, that wouldn't have affected me. I live a long way away from the university and I'm willing to travel because it's very important to me. Well, that's true. That is, not everyone is affected the same way by proximity. Very motivated, very talented students are probably less impacted by proximity. The students who are most affected are what we might call marginal students. They're just saying, should I go? Should I not go to a higher education? For them, the choice is not as clear. They're more on the borderline of the choice. For a student of that form, a close university that has lower cost of attendance, that for them, it might be a substantial effect. So this is where this idea that proximity may affect our choice is not always useful to think about introspection, think about what we have done, but to think about other people and who is most likely affected. Some people will be affected by this, but not necessarily everyone, and that's okay. So what did David Card do in this paper? He had a data set that turned out to be all men. Just to be clear about this, it was individuals. This is a data set from the 1970s, quite old data. But one of the variables that was available in this data for each individual was the location where they were raised, where they lived when they were young. And that data was in the form of the county of residence. Now, if you're not familiar with the term, the county in the United States is a regional administrative unit. It's different than cities. So the United States is divided into states. Then every state is divided into regions called counties. So everyone is uniquely assigned locationally to a county. So we know what county you live in. For example, I live in the county called Dane County, which is the name, okay? And then since we know now the county where a person live, we also have another data set which shows all universities and colleges in the country, and that each university and college is located in a county. Some counties have universities and colleges, other counties do not. The county I live in obviously does has the University of Wisconsin where I work, but then the neighboring counties do not have universities, the counties that are neighboring Dane County. So these are places that are approximately, say, 1 hour drive away. So we can then, by matching these two data sets, we know for each individual whether or not the county they lived in had a university. And that's basically the deal. So his instrumental variable that David Card used was whether or not you grew up near a college. And near in the data meant in the same county. It'd be more ideal if we actually had a distance measure, but this is what he had. So in terms of the math, the basic equation is y equals alpha beta x plus e. That's a causal equation. But then we also have an equation for x. X equals delta plus gamma z plus u. So here x is education level and z is proximity. In this case, it's a dummy variable, 0, 1. And we would guess that gamma, this is now the core coefficient for the instrument, that gamma is going to be positive. That is, if we are near a college, we're more likely to attend education. Therefore, on average, our education levels will be higher. That some people will then be motivated to attend college. That will increase average education levels. An instrumental variable estimator measures the impact of how exogenous variation gamma z, the exogenous variation gamma z in x, how that impacts y. So that the instrumental variable estimator doesn't just look at the structural equation, but it looks at the instrument equation and measures how this exogenous variation, the change in our proximity, impacts the education and thereby impacts the outcome y. And that exogeneity, that is allows us to measure the causal effect beta. And so now I won't go through the math of the estimators, it's pretty standard, but what does David Card do? He does a least squares regression, a log wage on years of schooling, and finds a coefficient of 0.07. Now, how do we interpret this? And it's always important when you do a regression estimate to think about what it means. And here, education is measured in terms of years of schooling, and the left-hand side is the logarithm of wages. So then the coefficient represents the percentage increase for 1 year. So this 0.07 represents an approximate 7% increase in wages for every year of education. And if you think about that, that probably corresponds with some intuition about that if I go to university for 4 years, that might correspond to a 27-30% increase in wages. It's not too unreasonable. But what if we use this instrumental variable estimator using the instrument of college proximity? Then Card found that the coefficient was 0.13, which represents a 13% increase for every year of education, or that's just close to approximately a 50% increase in wages for 4 years of university education. A much larger impact, substantially bigger impact, saying that education is more valuable from a causal viewpoint than we may have thought of before when not using the causal estimator. It's also not, this coefficient is also less precisely estimated. The standard error is about 0.05, indicating there's a lot of uncertainty in the IV estimate. And that's one of the challenges with the causal estimates. Typically, you're getting a better estimate in terms of centering, but the uncertainty in the estimate has increased. And that's part of the honesty at the confidence interval. So it's a big standard error, meaning that we don't measure this effect very precisely in this data, but it does suggest that it's a larger effect than we would have guessed from looking at least squares, which we know is a biased estimator. It's important to look at the reduced form. Now, just back up. The reduced form is the second equation, the equation of x on z. So if I just look at that coefficient is 0.33 with a standard error of 0.08. So what does that tell us? It says that living near a college increased average education by about 0.3 years. Okay, so it doesn't mean that every individual lived near a college went and had education of 1/3 a year more. One way of thinking of it is perhaps 1 out of 3 people is impacted by this living near a college, and they attend for an extra 1 year, or on average, maybe out of every 12 people, 1 attends the university for 4 years. So if you take 12 people, move them from a village to a city near a college, about one of the 12 people will end up going to college, and the other 11 will be not affected by this movement. So this is a small amount. It's non-zero, but it also accords probably with your intuition that most people won't be altered by where they choose to live, where their parents raised them. But some people are impacted, and that some people is large enough to be a non-zero effect. And then we can look at that causal effect. Now, how do you interpret these IV estimates? This is probably the biggest thing for a, so I'm talking about here, how do you write an empirical paper? And so what you're interested in this example is looking at what is the impact of education on wages. And what Card made the case that we can measure this effect by looking at proximity as being a valid natural experiment. The natural experiment is that you had no impact over where you grew up. It was impacted by choices your parents made, perhaps for historical reasons, and it's completely exogenous to you. And so when you write the paper, you have to spend a fair amount of time making the credible case that this instrument, in this particular case, college proximity, is exogenous to the outcome. The outcome is a person's wage they receive as an adult, and that you have to make the case that where you grow up, your location, is a natural experiment. It's something that varies exogenously to your true abilities, and that the only way it's impacting your outcomes is through this indirect effect that college proximity, while it might be exogenous to you, it does have an impact on you in the sense of the likelihood that you get educated. And so with more education, you will end up receiving a different kind of job and thereby receiving a different kind of wage. So a researcher needs to verify that the instrument has a, and one of the things you also need to do is to verify that the instrument has a non-negligible effect on the endogenous variable. Otherwise, you have an invalid instrument in the sense of being too weak. But under these two conditions, the IV coefficient can be interpreted as a causal effect. Another thing which comes up in IV estimates is the so-called late or local average treatment effect interpretation due to Angrist and Imbens, and to recognize that causal effects are heterogeneous. Not everyone is impacted the same way by education. But in that case, the IV coefficient that we estimate is really for the subpopulation of compliers. I'm going to jump over this very quickly, but what is that? Those are the individuals who are affected by the instrument. So let's focus on this particular case. We mentioned that the reduced form estimate is consistent with the statement that if I take 12 individuals and I move them from a village to a city with a university, that on average, one of those people will end up going to the university. Okay, the IV estimate of 13% causal effect of educational wages is for that one individual, not for other people. The estimate is saying for people who are moved from villages to cities and are motivated by that to attend university, those are the people who are measuring the effect of through the instrument. Because we've taken 12 people, we moved them conceptually through the natural experiment from the village to the city. 11 don't attend university. One does. It's a difference in their wages that we're able to effectively identify the impact of education on wages, and that is the population that we're able to that really that 13% number is really talking about. It's not talking about the impact of education on wages for a person who would have attended a university regardless. So once again, going back to the particular number, 13%, it seems like a large number, but here the card's estimate is saying that these people who are on this margin, who are marginal decision makers, that they will go to university if they live near one but not otherwise, they have a big impact on their wages when they go to universities. This is a strong motivation in terms of policy to have colleges everywhere, to make sure everyone lives close to one, so everyone gains this benefit. Okay, that's the first story. Now I'm going to make a second story, also talking about wages in a way, but it's a different look. It's looking at the impact on employment. Minimum wage. This is referring to a famous paper, also written by David Card, jointly written with Alan Krueger in 1994, where they introduced largely to economics idea of the differences estimator, which is a really go-to method now for writing empirical papers in economics. So in many places, including the United States, there are government mandated minimum wages. So the government says, if you work, you must make at least this amount of money. If you employ someone, you have to pay them at least that much, and any wages beneath that level are not legal. Economic theory, we teach this to principles of economics students, says that if you have some sort of a minimum wage, then employers are going to try to hire fewer people. More people will ask for jobs, and we'll get an imbalance. But the main point that comes up is really the upward sloping supply curve, the downward sloping demand curve for labor, and such that says that you raise the minimum wage, that employers are going to hire fewer people. Well, where will the impact be greatest? It's going to be impact among low-skilled workers, low-wage workers. Those are the people on the margin are the ones who are having the greatest work. And so standard economic theory often says, don't employ a minimum wage because you're going to hurt the people who your goal was to help the most. But the empirical question, the question an econometrician would ask is, well, what is the magnitude of this effect? Is it small? Is it big? If it's a small effect, maybe it's not that big a deal. If it's a big effect, okay, that's important. So Card and Krueger set out to answer this because in 1992, the state they lived in, New Jersey, it's a state where Princeton resides, where they were working at the time. New Jersey mandated an increase in the minimum wage of a very substantial amount, went from about $4 an hour to about $5 an hour. So this was 30 years ago. Put in the context, this was at the time a substantial increase in the wage. And so a reasonable question is, did that have an impact on the amount of employment? To focus in, they looked at fast food restaurants. So this would be McDonald's. You've probably heard of McDonald's. McDonald's and similar restaurants pay small wages and typically minimum wage. And at the time of the survey, about 30% of the individuals in the sample were paid the minimum wage. So indeed, this is a population of people who are either paid the minimum wage or slightly above that. So they surveyed, I think they simply called up a bunch on the phone, a bunch of fast food restaurants, and asked them a bunch of questions, including how many employees do you have, how many hours they work, what are the prices that you charge, and what are the wages you pay. And what did they find? Okay, so they did two surveys, one before the policy change and another survey after the policy change. So they set out a survey, they found out how many employees the restaurants had, and then waited half a year, the wage went up, and then they surveyed the same restaurants again, asked them, how many employees do you have? They found out that before the policy intervention, there was an average of 20.4 employees per restaurant, and after the increase, there was an average of 20.9 employees. The economic theory had suggested that the number of employees should have fallen, but the number of employees actually increased. Wow, this suggests that employment increased due to the policy change, the contrary of what one would have expected from the economic theory. Making this comparison is called a difference or difference estimator. And the problem with it is that there's no control. It's unclear if the change is due to the treatment or if it would have occurred anyway. Maybe people simply were eating more hamburgers and that there would have been an increase in the demand for fast food anyway. So the difference in differences estimator is focusing on idea of a control group. We want to have a control. We want to have a counterfactual group of trying to get at what would have been the change of employment if there had not been this policy change. And these authors said, we will use the neighboring administrative area, the state of Pennsylvania. So if you know the geography of the United States, there's a state of New Jersey, which is a relatively small state. There's a big state called Pennsylvania to the west, but they focused on the eastern counties of Pennsylvania. And Pennsylvania in this time period maintained the same minimum wage policy of $4.25 an hour. They had no policy change. And the area is very similar to that of New Jersey. It seems this is a comparatively similar geographic area. So Card and Kruger surveyed 79 restaurants in eastern Pennsylvania. And what did they find? So this is the standard diff and diff table. So I mentioned before that New Jersey had average employment of 20.4 and 20.9 before and after the increase. Simultaneously, they did the survey in Pennsylvania at 23.4 versus 21.1. And that in contrast to New Jersey, employment actually fell in Pennsylvania. So this is the control. This is the idea is that if there had been no policy change, employment actually would have fallen. So you add these two together, a positive and a negative, and you get a number of 2.75. And you can take the difference and differences either way. So what comes from this is that Card and Kruger say is that the difference in difference is actually a positive number, 2.75 employees. So this is a stunning number because it goes contrary to economic theory. So it's a very strong increase. Here now, really the economic concept is to think about what is the control we're talking about. We're treating Pennsylvania as a control. So that's really the valid issue in causal inference. Was Pennsylvania a valid control? So their argument is that employment trends should have been similar to the two regions if the policies are identical, and we can therefore use the employment trend as a estimate of the counterfactual employment trend in New Jersey if there had been no change in policy. And therefore, we get what is called the difference in difference. And what's really key is that we're looking at the change in one place relative to the change in another place with the idea that that other place is a valid control. Now, the simple example just presented is very, very simple. It's more general to have not just two states, but multiple states, and not just two time periods, but multiple time periods. And how can we then have that as we write it down as a two-way panel data model effectively? So on the left-hand side, I have the outcome for individual, which an individual in this case is a restaurant at time period T, a linear function of the state of the restaurant, New Jersey or Pennsylvania, time, there was two time periods before and after, and the dummy variable D is a policy variable for the change in the minimum wage. which in this particular example is actually can be written as the interaction of these two dummy variables. So you can get the same effect. The policy effect is theta by doing this linear regression. And I'll show you it right here. This is, if I do the linear regression estimate using the same data, I regress the outcome employment on an intercept, a dummy variable for the state, a dummy variable for the time period, and a dummy variable for the policy. And I get exactly the same number, 2.75, as I did by looking at the table. But now I also get a standard error. And so that's the neat thing about doing the regression approach. One of the neat things is that you get a standard error. And also, this is easy to generalize to the context of multiple restaurants and multiple time periods. This is called a two-way fixed effect model. And the general notation is regressing y on an individual effect, a time effect, and a policy. So I'm regressing the outcome on the policy, both with an individual effect and a time effect. This is estimated by what's called the within estimator. Just standard, this is kind of bread and butter, basic panel data econometrics, but it can be interpreted as a causal effect in the context that we've described. Briefly, you have generalizations. We have multiple time periods, multiple units, etc. The big thing I want to get at is that I want to interpret this as a causal effect, and that isn't obtained simply because I did a two-way fixed effect regression, but it's obtained when I can think of the policy effect as being exogenous. And here's the idea that this increase in the minimum wage is a quasi-random natural experiment. What's the concept here is that the policy, the minimum wage, cannot be in response to market conditions. Thinking about this, it's not so clear that this example works. Is it the case that really the change in the policy had nothing to do with the world that was going on? That's not really credible. Policies always are part of the world we live in, so they probably are not truly quasi-random. This is generally a weakness in empirical DID studies. They typically look at policy variation, and it's hard to believe that true policies are really random experiments. More likely, they are decisions by reflective policymakers. Anyway, the way to think about this always is that the policy intervention that you're using to identify a difference in difference is analogous to an instrument in an instrumental variable regression. In the card example of the effect of college proximity on wages, we were trying to take analogous seriously the concept that where you lived is an exogenous variation that can be used as a natural experiment. In the difference in difference example, we had to be thinking that the policy is a valid exogenous variation, a natural experiment that can help explain the outcomes. And that we will have a causal effect when that assumption is valid. If that exogeneity assumption is not valid, then it's not a valid causal instrument. Now I want to quickly go through my third example of causality, which is regression discontinuity. And I'll be using the example from the paper by Ludwig and Miller in 2007, a very nice example, which is the effect of a policy called Head Start. Now, this is a very United States specific policy. It's a very narrow oriented policy, so I will have to describe some of the institutional details. In 1965, the United States government embarked on a campaign to try to improve poverty, anti-poverty programs. And this Head Start program was particularly well known of focusing on providing services to families and children aimed at young children in poor families. So it was aimed at children of the ages 3 to 5 and their families, and providing services that were thought to be most beneficial at improving outcomes. Okay, now without going through the details of the specific programs, what we're going to be looking at is the question, did it work? Did Head Start change things? Okay, now there's lots of outcomes that we could have of interest. Ludwig and Miller looked at several different outcomes. I'm going to be focusing on one specific outcome, mortality. That's a pretty big outcome. Do people die? Okay. So mortality is the outcome being that children died at a lower rate due to this intervention. Okay. So, but there's other outcomes you also can look at that, for example, but like wages or other things. But here I'm looking at the specific outcome of mortality, and we're going to be looking at this empirically. Because again, this is a question we all feel this is a good thing to do to provide services, but the question is, did it have an effect and how much? Okay. And the data that they looked at is looking at the funding that was provided by the US divided up by US county. But if you just looked at the correlation of funding and outcomes, you would find a positive correlation rather than a negative correlation, because funding is targeted to poor counties. In other words, if you're a poor county, you are going to receive more funding, but the outcomes are also going to be bad. So that doesn't, that correlation is not going to tell you what you want, which is whether or not there's going to be a causal improvement. So how did they break this impasse? They looked at the fact that there was also a process by which funding was granted. It wasn't just granted to poor counties, but it was based on grants. The local county had to ask for this money. They had to submit an application through a grant. Okay, so that they had to make a request. And then to help the poor counties, the U.S. government provided grant writing assistance. They sent in specialists that said, here's how to apply for this grant. To make sure that the poorest areas in the United States receive the best funding, the government sent this grant writing assistant specifically to the poorest counties. So they realized they could fund money for 300 counties. They ranked the counties in the United States from the poorest to the richest, and then took the poorest ones and sent the assistance to those groups. That was how they were selected, and how they select poverty is based on the 1960 U.S. Census. So that was 5 years aged data at that point. So what's coming here is that poverty predicts both bad outcomes and the funding, but here it's going to be an exogenous variation, which we can use to look at the likelihood of receiving a grant. The key is that the government provided this assistance to the 300 poorest counties. If you were 299th or 301th in this ranking, you're effectively similar in terms of poverty ranking, but the one that's 299 received the funding, the 301 did not. So there was this arbitrary distinction between counties based on their poverty rate, but that would have could receive a substantial effect on their likelihood of receiving this funding, and therefore the outcomes. And this is the natural experiment is induced by this policy rule that had a discontinuity in the rule based on the poverty ranking of a county. So the regression discontinuity estimator looks at outcomes as a function of the poverty rate with a discontinuity. And so in this application, they look at the mortality of children, young children, due to things like tuberculosis in the 1970s. And so this is 8 to 18 years after the grant writing intervention. So this is trying to look at the long run impact, and they're trying to look at the impact on mortality. So in the language of regression discontinuity, we have observations, in this case, counties. The outcome is the mortality rate. The so-called running variable or regressor is the poverty rate. There's going to be a cutoff. In this case, it's a poverty rate for the 300th ranked county. We have an intervention variable, which is this grant writing assistant. And in the regression discontinuity design, it has to be a deterministic function of the running variable. Here it's the indicator function that the poverty rate is bigger than the cutoff. And we're interested in the regression function, which is the impact of the poverty rate on mortality. We understand this through the potentials outcomes framework that says that you could have had an outcome if there had been no intervention. There's the outcome if there is the intervention. There's the M0 is the impact on poverty when there's no intervention. M1 is the impact when there is an intervention. The observed regression function is a combination of these two, and I think it's easiest to see this in the picture. So I'm going to jump to the picture. On the right hand, the X variable is the poverty rate. This is in general, it would be the running variable. And the dependent variables on the left-hand side, and what you see is that the regression function is increasing up to the discontinuity, the cutoff, and then it's increasing again. And why is that? Is the dashed lines represent the regression function that would have occurred without the intervention and with the intervention. But what we only see is the regression function for given the particular intervention. And that's the theoretical description, but then the data might be more interesting. On the x-axis, I have the poverty rate. So like 20% says that 20% of the population is impoverished. 80% means that 80% are. So this is very, very poor counties. 60% is the threshold. So counties where 60% or higher, the families were in poverty, they receive this extra assistance. And for counties on the left side, they did not receive assistance. Then we do a regression, a non-parametric regression of the mortality on the poverty rate, and we see that it's increasing. That is, the more poverty there is in a county, the higher the mortality, the higher the rate that children die, unfortunately. But suddenly there's this discontinuity that when we hit 60% poverty, suddenly the mortality rate drops down a lot, but then it's increasing as the poverty rate increases from 60 to 80 with some nonlinearity, but these confidence bands, the shaded area shows that there's a lot of uncertainty in the estimates. But the big thing here is this big jump, which says that you go from 59 to 60 in the ranking and the poverty rate. Suddenly you have actually a big decrease in mortality. That's the impact of this Head Start funding. Is the impact isn't the order of a bit more than one death, and this is deaths per 100,000 individuals. It's a huge impact. So it's saying that the we can look by this discontinuous effect and identify the impact of the anti-poverty program by looking at this quasi-experiment. The quasi-experiment is saying that this division of the counties at that boundary was effectively arbitrary. Effectively arbitrary distinction leads to this big impact. I'm going to jump over this. The estimates are doing non-parametrics, but here I just wanted to describe very briefly what is the core here. The core is that this treatment is exogenous. So I've mentioned this again and again, that for the instrumental variable framework, you need to have an exogenous impact, a variable which impacts us so that we can treat as being external to the individual. For the difference in difference example, the policy has to be exogenous to again, the outcomes. And the same thing in the regression discontinuity design, it has to be that this treatment is a function only of this running variable, and therefore is not something which is endogenous to the outcome. And then we can interpret this measured RDD effect as a causal effect, and we're really thinking this is analogous to a natural experiment. So I've explored 3 stories in what I'd call causal economic inference. I've looked at the effect of education on wages, the effect of the minimum wage on employment, and the effect of this anti-poverty program, Head Start. Each story describes an econometric method instrumental variables, difference and differences, regression discontinuity. If you look at the journals and the top economic journals recently, these three methodologies dominate a lot of the applied macroeconomic studies. Each method requires some sort of exogenous variation. In the case, the first example, it was an instrument, which was the distance from a college. In the second example, it was a policy, the minimum wage legislation that varies between New Jersey and Pennsylvania, varies across regions. In the third, it was a treatment, which happened to be the grant writing assistance, and which was not provided uniformly, but was provided based on a deterministic rule based on county level poverty. By being able to identify that specific treatment rule, we're able to identify an exogenous variation. All this idea of causal measurement in economics, all of them require some sort of valid exogenous variation. It's easy for me to sit here and say, you know, go find it. In practice, it's very difficult to do. So students will come and say, how do I find an instrument? How do I find a DID? But you just can't find it. You have to work hard. It's not going to be in any, just pick up a data set. You're not going to find an instrument. You're not going to find a exogenous variation. You have to search for it. And frequently it's going to come through a combination of different data sets together. But it's the core of a good economic research paper. A good economic research paper, you're going to identify a causal effect because you've identified an exogenous variation, and you're going to be able to make that case credibly in your paper through a variety of institutional and other explanation factors. And that's going to be what sells your paper or not. But once you've identified that exogenous variation, then and make that credible case in your paper, you have a good part of the path towards having a good paper that you can publish in a good journal. So that's it for my core talk. And now, if there's any questions, I'll be quite happy to talk about them.
Professor, thank you for excellent lecture. Can I ask you to comment on the alternative method, on how or where would you put vector autoregression method in the spectrum here?
That's an excellent point, and that would have been a fourth topic, but I even here with three, I ran out of time. Vector autoregressions are the go-to popular methodology in modern macroeconomic time series, and the key to identification in the vector autoregression is the identification of the structure. So it's moving from a simple vector autoregression to a structural vector autoregression, where you can decompose the shocks into demand shock, a supply shock, a policy shock. And I don't want to go into too much details about that, except that the debate typically in the structural vector autoregressive literature is how to do that identification, how to put the structure on the shocks. But this is all the very important causality story. Yes.
Once again, thank you very much for your time and the presentation, sir. Professor Hansen was our guest at the last open meeting from our series. As the president of the Scientific Association of Data Analysis, I would like to once again thank everyone for this academic year full of lectures and knowledge we were able to acquire. So thank you very much, and just have a great evening. And I hope to see you soon.
Well, then, thank you.